Hello, I am JD and you are listening to The Ongoing. Every day, almost half the food we eat exists because one industrial process, turning air into fertilizer. Fertilizer needs nitrogen. One of the most common forms of it is urea. And one of the best ways to make urea starts with a single chemical, ammonia. And the key ingredient needed to make ammonia has always surrounded us. It fills nearly 80% of the air we breathe. Nitrogen. This episode is the story of how we learned to turn that air into food. Something first made a few drops at a time in a laboratory and scaled up into a process that never stops, running day and night, producing it by the ton. Plants need nitrogen, one of the basic building blocks of life, used to build proteins, DNA, and chlorophyll. Without it, plants simply cannot grow. For centuries, farmers relied on manure, compost, and imported bird droppings called guano, so valuable that countries fought over it. But by the late 19th century, those sources were running dry, and the world's population was growing fast. In 1898, a British chemist named William Crookes stood before the world's leading scientists and said it plainly. Within a few decades, there would not be enough nitrogen in the ground to feed everyone alive. Widespread famine unless something changed. In the early 1900s, a German chemist named Fritz Haber decided to try something specific. React nitrogen with hydrogen directly to make ammonia. Both ingredients were already within reach. Hydrogen could be pulled from natural gas. Industry already knew how to do it. Nitrogen could be separated straight out of the air. That process already existed too. The chemical reaction equation looks easy on paper. And here's how it is. One nitrogen molecule plus 3 hydrogen molecules produces 2 molecules of ammonia. Easy on paper. But when Haber mixed the gases together, almost nothing happened. Here's why. Neither nitrogen nor hydrogen exist as a single lone atoms. Both travel in pairs. 2 atoms of the same kind bonded together. Hydrogen's pair is held by a single bond, easy enough to break. Nitrogen's pair is held by a triple bond, one of the strongest bonds that exists. For the reaction to happen, both bonds have to break. Hydrogens breaks easily. Nitrogens does not want to break at all. So Haber asked the obvious question. What if we simply heated the gases? Heat makes molecules move faster and collide more often, so the reaction, which had been sitting almost completely still, finally started happening. Ammonia began forming, but in a small amount. Most of the nitrogen and hydrogen passing through came out the other side unreacted, unchanged. To understand why, we need to learn something surprising about chemistry. There is a general perception that a chemical reaction works like a one-way street. Ingredients go in, products come out finished. But this reaction does not behave that way. Think of a revolving door. People pushing in on one side to get inside a building, and people moving out, pushing through the other side. Now imagine a hypothetical situation. The people moving in and the people moving out are happening at exactly the same rate. The number of people inside the building never changes, even though nobody has actually stopped moving. That's exactly what's happening here. Ammonia forming and ammonia breaking back apart at the same rates. Chemists call that a reversible reaction. And the balance point where it settles, equilibrium. Haber had reached that point. Some ammonia was forming, some was breaking apart, and the amount stayed disappointingly small. So Haber faced another question. How do you persuade the reaction to make more ammonia instead of turning back into nitrogen and hydrogen? Years earlier, a French chemist named Henri Le Chatelier had worked out how reactions like this one behave. How a reversible reaction responds when you change its conditions, and how you could use that to drive it in the direction you wanted. Haber used that idea. Raising the pressure, he reasoned, should push this reaction toward making more ammonia. He tested it, experiment after experiment, and it worked. Every time he raised the pressure, more ammonia appeared. He was not changing the chemistry. He was changing the conditions to push the reaction where he wanted it to go. This same idea explained the heat problem too. Heat speeds the reaction up, but only up to a point. Here's why. This particular reaction gives off its own heat as it runs, and that extra heat pushes the reaction backwards. So, past a certain point, more heat means less ammonia, not more. Heat helped the reaction go faster, but it also pushed it in the wrong direction. So heat was off the table as a way to get more speed. Haber needed another way, something chemists call a catalyst. A catalyst doesn't get used up, and it doesn't change where the reaction settles. It just gives the molecules an easier way to react. So the process speeds up at the same temperature. In the presence of the osmium catalyst, nitrogen and hydrogen reacted at nearly 3000 pounds per square inch and past 500 degrees Celsius, ammonia began forming. In 1909, that reaction ran continuously. One of the great laboratory breakthroughs of the century. The idea was proven. Haber also had a small working loop recycling the leftover gas. A complete working blueprint right there on a laboratory bench producing ammonia by the drop, by the gram. What came next was taking that same process from grams on a bench to tons a day in a working factory. From here, the story stops being chemistry and becomes engineering. Carl Bosch, working at BASF, inherited Haber's laboratory success. But proving an idea in a laboratory is very different from making it work inside a factory. The chemistry was solved. The engineering had only just begun. Bosch had to make the process run every minute, every day for years at 1,000 times the size. And at that scale, conditions merely difficult in a lab became dangerous. The first problem was not the chemistry anymore. It was, how do you keep these gases under control at all? 3,000 pounds per square inch of pressure is roughly 100 times the pressure inside a car tire. And over 500 degrees Celsius, with hydrogen working its way into anything it touched. Ordinary steel did not hold. It cracked, went brittle, failed. Bosch needed something that was not necessarily the strongest material available, but one built specifically for this reaction. Something that would not blow up. They built the reaction vessel in multiple layers of steel, each layer configured differently, solving the problem so that the whole thing was safe to run day after day, year after year. This reaction never fully completes. There is always some nitrogen and hydrogen left unreacted. So just like Haber's recycling loop, these leftover gases were compressed and sent back into the reactor, just at a much larger scale. Osmium was too rare and too expensive for a factory. So Bosch's team looked for something else. They found a simple iron compound instead. Cheap, easy to make, almost as good. It is still what's used today. By 1913, the first industrial Haber-Bosch plant began producing ammonia, roughly 20 tons a day within the first year. Today, the world produces well over 170 million tons every year. This ammonia gets converted into urea and other fertilizers, the forms that actually reach a farmer's field. Nearly half of the nitrogen inside your body, your muscles, your DNA is estimated to have passed through a Haber-Bosch reactor at some point. It is impossible to say exactly what the world would look like without it. Maybe we would have found another way. But by most estimates, this one process reshaped how many people this planet could actually feed. Haber unlocked the chemistry. Bosch made it run safely and continuously. Between them, they turned a laboratory experiment into one of the greatest engineering achievements in history. That's it for today. Thanks for listening. I am JD, and this is The Ongoing.